Hello, my name is Thomas Schwingle, and I'm a professional cinematographer based in Los Angeles. This video was made with the generous help of one of my favorite rental houses in Los Angeles, CSLA. They gave me their full support in shooting the tests for this video, and as you'll see here soon enough, their custom, one-of-a-kind, only set in existence, Helix Primes, were exactly the design of lens I needed for this video's topic. The development of this video has been a journey. Many months of research and digging through scientific articles, forums, videos, and even watching some online physics lectures from college classrooms. I started this in October of 2024. I was ready to start narrowing a script for the video in January 2025, but the LA area was dealing with the wildfires. I had volunteered with a wildland fire department for many years in the greater LA area, and while I was no longer an active firefighter, I was sought after for help. That derailed the focus on this video. Then I had to get back into some of my usual cinematography work. Every now and then, in online forums, I see questions like this. What causes this effect? Why is there a pattern inside this orb? How do I do this? Why is this orb not all there? All of these questions point to the modern photographic idea of bokeh. If you haven't found this popular online video yet by Pro Gear News, it has been a reference for many people on how to correctly pronounce the Japanese term bokeh.
Bokeh, bokeh, bokeh,
Bokeh.
bokeh. That's going to be a bokeh.
I, like many others, used the English mispronunciation of bokeh. I'm going to try to use the correct pronunciation in this video, but it does feel a little strange after using it wrong for so many years. Kind of like the whole Ari pronunciation debate. Both ways are used in Ari's advertising web videos.
I'm a lens specialist at Ari in Burbank, California.
Ran with Ari.
Hey there, I'm Sean from Ari.
Senior Product Manager at Ari Lighting.
But bokeh comes from a language and not from marketing, so I'm going to try to honor that. Bokeh is a transliteration from Japanese. Its meaning is similar to confused or dizzy, to space out, be unfocused. As I've researched it, the original use of bokeh in photography was to describe the aesthetic quality of an image's blur, the flavor, taste, or pleasantness of it. It started as a niche photographic term in small creative circles, but now in the age of digital and user-generated content, to the general layperson it means out-of-focus Christmas lights. Go ahead and do an image search for bokeh. All you get are colorful orbs. However, the idea extends to more than just out-of-focus bulbs. A bright spot in an image is the obvious and easy thing to point at, but there are other ways that out-of-focus areas are rendered by lenses, and these too can be part of the aesthetic. Bokeh opens the door to talking about other areas of lens optics, as it relates to parts of the image that are not in focus. Aberrations, depth of field, circles of confusion. We choose lenses for our projects based on their characteristics. How sharp are they? How do they render skin tone? What does the focus fall off look like? How does the lens handle contrast of light or color? Usually the in-focus area of the frame, the actor's face, the wide panorama scene, the product shot, these are the most important because this is what is usually telling the story and what will be the driving elements of our scenes. But every lens characteristic we consider will also affect the areas that are not in focus. This starts us down a path of consideration as cinematographers. What do we need to know about the out-of-focus areas of an image, and what control do we have over it beyond what the chosen lens gives us? In many online lens tests, there's often an element to test for the modern idea of bokeh. Usually a string of lights, and sometimes people use some sort of flashlight to test for flaring. Honestly, if you pick a random lens test online, you'd think everyone was preparing for a project that was about a burglary taking place at Christmas time. Turns out, however, that if you know what you are looking for, a tiny, bright, out-of-focus spot of light can tell you a lot about a lens's characteristics. I think some people just mimic other tests they see, but I'll try to show you what you can look at and learn from. For decades, even centuries, lens designers were on an advancing journey to make lenses sharper, better, faster, and with less character, which is sometimes a word we now use for a lens's aberrations. Evolution of technology allowed optical engineers to improve upon previous designs. Then, when recording images transitioned over to digital capture, we got to a point where electronic systems could record and perfectly transfer, now almost infinitely, images in much finer detail than physical film grade could, and copies can be made with perfect fidelity. The great advancement of these modern, clean, optically superior lenses and transfers felt too perfect to some filmmakers when viewed on our also now superior screens, monitors, and projectors, and especially when compared to classic cinema, shot on older tech lenses and upon the random pattern of film grain. And so there's been a movement to use older optics, embracing all of their aberrations, or design new lenses that permitted some of the old aberrations to exist, albeit in modern, sleek, mechanically advanced housings. So we've moved forward technologically, and now, for artistic reasons, including the bokeh, there are sometimes controlled artistic steps back into the areas of imperfection. But why does this happen? Or why does that happen? I've spent hours totaling into days of time studying lens optics over the past 6 months, and I have to say, next time you meet a lens designer, optical engineer, or technician at an event or a gear expo, shake their hand. The physics, science, and pure math of everything that goes into these tools that allow us to make art, it's really impressive. After all of this research, I can make multiple videos explaining types of aberrations, depth of field calculations, physics of optics, anamorphic design, glass coatings, lens element groups and designs, so many topics about glass. I don't think that will be fun, and there are many videos out there that have tackled parts of these topics, and probably better than I want to at this time. What I hope to do is distill all of these optical concepts into useful ways we can think about image control on set, with tests and examples. So very basically, what are we doing when we use a cinema lens? We're using a combination of predominantly, usually, glass elements arranged inside an advanced housing to collect the reflected light of the three-dimensional world in front of the camera and then focus that collected light onto some sort of image recording surface, film grain or digital sensor, etc. If you didn't have a lens, you would have light coming from everywhere hitting your sensor with no way to focus it, control it, or shape it into something your eye would recognize. Look what happens when I point this active, open digital sensor around. Oh, that's Fireball. He's assisting me today. If I point the open digital sensor at this red beer tub that Fireball claimed for himself many years ago when I was setting up for a party and it now just lives here, we get a red image, but it's unfocused. And if I pop in this orange yoga roller, same thing, only orange light, if I am close enough to the object. Only unfocused orange light is reflecting back. Now if I use my fingers to form a crude pinhole over the sensor, I can make a very rudimentary image of Fireball in front of my patio door. Things come into focus a little when I shed away extra photons. And let's move up the ladder one more step. This is a magnifying lens I bought at the dollar store. We would call it a simple lens in optics. It only has one element. I had to find its focal distance ahead of time, and I made a brown paper housing around the lens to block out extra light coming in from the sides. Real pretty. If we look through the front, we can see the ground glass of the DSLR being projected through the simple lens. It's not high tech, but it does form an image. Here's Fireball modeling for us again. The image is full of aberrations. You can see unfocused color bleed next to areas of contrast, and sharpness is definitely lacking. But some early consumer-facing lenses on little all-in-one cameras were like this, although usually at a wider focal length. Most lenses we use are spherical, so called because their shape is part of the surface of a sphere. There are anamorphic lenses for cinema, which use a cylindrical element, and while I will talk about them a little bit, most of this discussion in this video will presume we are using a spherically designed lens. The word lens has its origin in the Latin word for lentils, those legumes that are part of the Mediterranean cuisine. Lentils have a convex shape, so that's why their Latin name was also used for glass in the same shape. The collection of light, or field of view, of the lens is a conical shape owing to the spherical nature of the lens. The light passes through the elements, is inverted, shaped, manipulated, and is projected out the back of the lens, and in photography, captured. We start to get into complications because we are taking a spherical slice of the world and trying to record it onto a typically rectangular capture site. Think about your eyeball. It has a lens, it focuses the light of the 3D world, and it is recorded by your retina, which is also spherical where it receives the light. A spherical lens and the physics of its manipulation of light would operate best if the capture surface behind it was curved. While there are some cameras that are designed to curve a roll of film, like this Widelux model, that type of design was not practical for cinema film moving rapidly through a gate. In cinema cameras, capture areas are flat and rectangular. This mismatch of a spherical lens with a flat capture surface is why some prominent image degradation can result. We call these degradations aberrations in optics. This image I showed you earlier, while this swirl is often sought after as a creative choice, it is actually an aberration. The lens is not giving a fully accurate representation of the 3D world because the design of the whole system is not ideal. The 2D image that has resulted is not how the scene actually exists. But sometimes we like that as a storytelling device. Technically, film emulsion is three-dimensional. It has layers of light-sensitive silver halide crystals, and photons pass through those layers to record an image. And even our modern digital sensors, CCD or CMOS or otherwise, are made up of millions of photosites, which aren't flat but may contain little lenses mounted above them to help collect light, or even extra layers of sensor glass that filter different wavelengths, such as infrared, UV, etc. In both cases, these layered capture areas have dimension, but we ultimately translate that image into a 2D viewing experience, whether onto a film screen or the screen you are looking at right now. Point being, that little bit of extra depth at the capture site can induce some aberrations too, which I'll explain soon. What are all the aberrations? There are many. Some are obvious with old lenses designed with outdated technology, and some may only be found by the knowledgeable person who knows what to look for inside of an image. I will discuss some of the more blatant aberrations, where they come from, and what you can do about them, if anything. The variation in capture site and method can explain why lenses that were considered acceptable for film stock years ago, a medium that degraded the image with copies in use, those images may now appear not as sharp or wonky when paired now with a digital sensor. Sometimes that degradation is desired, and sometimes it might be unacceptable if blown up faithfully onto a 98-inch 4K television. We should now talk about depth of field and circles of confusion. I'm going to assume that you as a viewer are already familiar with depth of field and at least marginally familiar with circles of confusion. When a lens brings gathered light into focus at a point onto our sensor, the image taken from that part of the scene is deemed sharp. The areas of light that don't come into focus exactly at the recording plane are considered soft or out of focus because they aren't points of light. They are blobs of unfocused light. They are circles of confusion. At some degree along the rays of gathered light that we, the image makers, have to decide upon, the circle of confusion becomes small enough that we consider it a point and thus now in focus. The problem with calculating depth of field is that it is an arbitrary number. Whether a small blob is in focus or not can be subjective, and whether or not the blob has even illumination, if it's affected by aberrations. We have all of these apps and calculators we can use to determine how much of the image is in focus. Here on the commonly used app, Pcam, you can see they have a default circle of confusion for each camera system, which is only a guide, and you can customize it. But what size that circle of confusion should be isn't a firm rule. It depends on where you will ultimately view the final image. The best way I can explain it is if you have a thumbnail of a scene. Here it is, looking sharp. But when you blow it up and examine it, most of the image is out of focus. If I was looking at the scene on a large theater screen, it would be unacceptable. But here, when viewed at a smaller scale, it appears in focus. This image is in focus at one scale and out of focus at a larger scale. The blobs of light are acceptable to view on, say, a smartphone, but unacceptable when viewed on a theater screen. This is why when we pick lenses that are artistic or have heavy aberrations, you should have an idea of where it will be viewed. Of course, a cinematic 70mm VistaVision experience like the Brutalist can also be watched on your iPhone. I don't recommend that, by the way. But if you are the cinematographer, which choice do you make? It's harder to determine now with so many ways to view things. Let's talk about an aberration called field curvature because it relates to this discussion of depth of field and circles of confusion. We now understand that the spherical lens would be better used against a curved capture surface. Since we don't do that in cinema, we must force the lens to better focus its gathered light onto a flat area. We cannot physically force the conical area of gathered light to flatten perfectly against our sensor and be a great image with perfect rendition all the way across. There are going to be some sections of the scene that resolve sharper than others. This is field curvature. The physics of bending light from a sphere onto a flat surface come with sacrifice. Roger Sakala from LensRentals.com says you can do a quick, cheap test of field curvature by shooting a field of grass and then using Photoshop's Find Edge filter. In this example, even though the lens is focused at a fixed distance, not everything that is at that distance is in focus. Think about that. You are a camera assistant and your measurements tell you that the actor is 9 feet away. But not everything at 9 feet away may actually be sharp. If the actor is towards the right edge of frame, in a conversational shot, perhaps the focus there in frame is actually sharp at 8 feet and 8 inches and not 9 feet. And if you're doing splits, trying to hold focus for two actors at different distances, it might be that an actor can move laterally from an area of the lens that is in focus to an area that is out of focus. Field curvature isn't always a simple arc. It could be wavy. So a big gotcha in a lens that has a steep field curvature is that you have to chase the focus if the subject moves away from optical center. The area of best focus can be varied. Add the uncertainties around depth of field that I shared earlier, and you could be in for soft focus on a big screen if you rely on the wrong calculations. When in doubt, stop down. It doesn't fix the field curvature of a lens, but it will widen the band or depth of focus and allow you to be certain that your subjects are within that band. Field curvature is one of the many aberrations that designers try to control for when making lenses, but all aberrations have trade-offs. If you try to perfect one problem, you may be giving up ground in another area of the optical system. And the degree to which the aberrations are showing up can change based on where the lens is focused, or where the focal length is set on a zoom lens. Think of it like when you design a character in a role-playing game. You can only design your character to have certain levels of skills. More skills over in one area takes away the currency to have skills in another area. Related to field curvature is astigmatism. I found it to be the most complicated topic to distill into simpler terms. In fact, whether you are talking about the blurring effect in a direction or the mapping direction of a sphere, the term can be inadvertently inverted. For those here to learn more about the Petzval Swirl, the casual term for this effect, astigmatism as well as the previously mentioned field curvature are two of the main contributors to this effect. Joseph Petzval was a Slovak-Hungarian mathematician and inventor. He made the first photographic portrait objective lens, and at f3.6, it was faster than other lenses of the time, allowing for snapshots of humans in as little as 15 seconds. Film speed was slower back then. The adjustments he made in his lens that allowed for faster photography actually made the field curvature worse, which shows up as you move away from the optical center of the lens. Not a problem for a centered portrait. The swirl effect that we call the Petzval Swirl is a throwback to the design of his first lens, and the term Petzval sum is the mathematical calculation of field curvatures of lenses, which we still use. A sphere requires different geometry. If you remember history class and projections of maps, you recall that every time you try to flatten our Earth into a flat book, there's distortion. Mercator projection, Robinson projection, Winkle triple. We need to map our lens a little bit like it's the Earth. Looking straight down through the optical center, the center point of the lens is the North Pole, if you will. It is our main point of concern. If you make lines going out to the edges of the lens from the center, like longitudinal lines on a globe, these are our sagittal lines. If we make the latitudinal equivalent, lines circling the pole of the lens, these are our tangential lines. The sagittal lines divide up the tangential planes, and vice versa. Focus can be curved away at the recording surface in either of these planes. When focus in a sagittal direction doesn't line up with focus in a tangential direction, you get astigmatism. The two field curvatures aren't creating sharp points at the same place on the sensor. Take a look at a simplified example. It's a basic sketch of a wheel. It has rims that circle the center and spokes that radiate outward. In a lens that is resolving both fields of the lens correctly, the wheel is sharp. However, if we have blurring affecting the sagittal track, i.e. blurring that affects the image from the optical center towards the edges, the spokes of the wheel are not sharp while the rims are. We only have tangential focus. If the lens isn't focusing correctly in the tangential track, i.e. there's blurring that affects the image ringing the optical center, then we have blurring of the rims and not the spokes. We only have sagittal focus. I had to reread the literature on this like 12 times while writing the script and is still confounding. Credit to a paper by Douglas A. Kerr that attempts to break down these terms. Typically, unless a lens is damaged or had a malfunction in the build, the center of the lens will line up both of these fields just fine. A sharp center, no astigmatism. But when the lens designer doesn't correct these fields into a place of good optical balance, then the focus of these fields can curve away from each other rapidly, especially as you move away from the center of the lens. And the effect can be exaggerated in areas that are deeper out of the field of focus. And that is primarily what you are seeing in a lens that has the Petzval Swirl. Sagittal astigmatism, where the image is blurring around the center point of the image, getting radically stronger as you move away from the optical center. This is also related to the field curvature of the fields of focus, which are more physics for another time. The opposite would be tangential astigmatism, a kind of warp drive zooming effect in the bokeh. Stopping down a lens, just like with field curvature, reduces the effect. But of course, if you're seeking the Petzval Swirl, you're going to want to shoot closer to wide open to get full effect. And if you want to control the effect and really exaggerate it, you rent these Helix Primes from CSLA. CSLA had these manufactured and designed just for them, and the lens has a tuning ring that adjusts the field curvature and astigmatism, which will induce a heavier Petzval Swirl if you want it. Let me show you. Here is the CSLA Helix Prime, and watch as I roll through the effect ring. Notice the edges of the frame especially. And if I shoot the lens at 3 different stops, f2.8, f5.6, and f11, you can see how a deeper stop limits astigmatism and curvature, as well as other aberrations. Why would you shoot these artistic lenses at f11? The image that comes out the back of a lens is a circle, an image circle, if it's not clipped by any hardware. It's usually smallest when focused at infinity. With the high quality standards required of professional cinema lenses, the lens doesn't necessarily have a top or upward direction. The lens is marked only one way and is meant to be mounted one way, but you should be able to turn the lens in the mount without any detrimental effect on the image, assuming the mount style is turnable. And camera assistants may mount the lens sideways or upside down if they need to see the markings on the barrel in a unique operating situation. This, of course, doesn't apply to anamorphic glass, as the image is squeezed by a cylindrical element in one direction. If I turn this Atlas Anamorphic Silver Edition, the image is now squeezed in the vertical direction, which is an artistic choice. Cinema lens manufacturers make sure that the area of best optical image covers the camera sensor. Since many aberrations get exaggerated as you move away from the center of the image circle, designers may design a lens that projects a much larger image than needed. Since we are usually cutting a rectangle from a circle, they may design a lens so that there is ample room between the image-taking area and the edge of the circle to cut down on aberrations like vignetting, chromatic aberration, field curvature, etc. If any of you have tried pairing older cinema lenses with a modern, larger sensor, like full frame, you may have learned that some lenses won't cover full frame, or only some lenses within a given set will cover it. This is why. A lens designed for Super 35 might have some extra image area outside of the designed S35 cutout from the image circle, but maybe not enough to cover full frame. And if it does cover, the corners might be funky with aberrations, which could be your desire, but lenses within the same set might have differing aberrations in the corners because they are never meant to be seen, which could mean your project has inconsistent character at the edges of frame. Did you know that Ari invented both the industry standard PL mount and the new LPL mount for full frame coverage and gave the designs away for free? It's so other manufacturers and lens designers would adopt it and make it more universal. The PL mount was designed for a time when film cameras were dominant, and those cameras had a spinning mirror in front of the film gate so the camera operator could see through the taking lens. There was a minimum distance between the back of the lens and the film plane, 52 millimeters. Lenses can be designed with less aberrations if the rear glass elements can be closer to the imaging plane. Now with digital sensors, there is no spinning mirror, so lenses can be built to sit closer to a digital sensor. The LPL mount also allows the rear element to be larger. This is good for getting the light coming out of the back of the lens to be closer to telecentric, which is the fancy way of saying closer to parallel. As a side note, we never want fully telecentric lenses in filmmaking because it removes perspective. When light comes out the back of the lens closer to parallel, you don't have as much vignetting, spherical aberration, chromatic aberration, and other problems, especially in the corners of the image. An older PL lens on a full frame, even if it covers the sensor area, likely has its rays of light spreading out the back of the lens in order to cover. This spread to the corners is where weird things can happen. Chromatic aberration can look like this, where colors fringe, especially on areas of high contrast. And vignetting is worse, for a few reasons. One, which you can see here, the light has to travel farther to the corners of the sensor and loses energy on that journey. Yes, even in that small distance, the rules of the inverse square law of lighting apply. So the image corners are darker due to physics. We're going to circle back to the three-dimensional nature of digital sensors. Film was an organic random medium, but it generally had the same physical design tolerances between manufacturers as it had to run through a ubiquitous film gate design across camera models. However, each digital camera manufacturer designs their own sensors, and those sensors can have varying layers of optical glass, filters, or microscopic lenslets over the top of the CMOS or CCD. This layer of extra material acts like an additional element to whatever lens is used. Perhaps an older Leica lens on its own is well corrected for imaging onto film, but on a digital S35 system, the proprietary filter pack on something like maybe a Sony sensor induces some color fringing when paired with that lens. Other types of vignetting can happen within the lens itself. A type of optical vignetting can be seen here. These bokeh aren't round, even though the super speed has diaphragm blades that make a round aperture, as seen here. But if I stop the lens down, the oblong, so-called cat's eye bokeh shapes are reduced to now reflect the round aperture shape. You can see them form up. This happens because when the iris is full open, light that is entering the pupil of the lens is entering at an oblique angle and is being cut by the physical lens housing. You can see that the steeper angle looking into the lens matches the cat's eye bokeh we saw in the image. Stopped down, the full aperture opening is now visible at this angle, and the Christmas lights are not as clipped anymore, which is why the bokeh returns to a round shape. However, the orbs are now smaller because a smaller aperture creates smaller bokeh, and likely a smaller image circle, FYI. Another form of optical vignetting can be seen in film sometimes when the orbs are cut. What is often happening is that a flag or hard mat is being used to cut down flare, but it is creeping into the path of the conical image space. Just like the cat's eye, physical vignetting is being created by the obstruction. If the eyebrow is holding still, you might not notice the slight darkening at the top of the frame, especially on a dimly lit scene, but you will see the cut orbs if there are points of light out of focus. Most interestingly, and this will apply to everything we look at going forward, if the orbs are out of focus in the background, beyond the field of lens focus, the cut in the orbs occurs in the same direction as the obstruction. But look at the orb bokeh on the right. These lights are closer to the lens, closer than the field of focus. The effect on the orbs are inverted from the occluding eyebrow. I have more to show you regarding the control of bokeh, but first I should discuss spherical aberration. A simple spherical lens does not bend the rays from image space in a way so that they all realign neatly at a flat image sensor. Instead, the rays create points of focus at different depths, like you see here. Marginal rays focus closer than paraxial rays through the center. What that looks like on screen is a softer image. We can roll through the field and see where the image appears most sharp, which we can call circle of least confusion, but we'll never have a crisp image because some rays are focusing either behind or in front of the sensor. Stopping a lens down will help improve spherical aberration to a great degree, though stopping a lens down too far can introduce diffraction, the distortion of light and reduction of contrast as light interacts with the surface of the aperture blades. A lens generally performs its best at 2 to 3 stops closed down from wide open, minimizing aberrations while not suffering extra contrast loss. If a lens has significant spherical aberration, it will appear in the bokeh. There are 2 general types of spherical aberration, undercorrected and overcorrected. We have a lens with spherical aberration, collecting the rays and refocusing them on the sensor. Rays that gather focus before the sensor are more concentrated near the optical center. Rays that bundle focus past the sensor are more dense near the periphery of the system. If we map the density of a point of light at cross sections, we can create these simulations of an image point's appearance as it travels in image space. This is a rough representation of what the bokeh will appear like if it's in the foreground or if it's in the background. Let's look at this TLS Rehoused Petzval 58mm on an ARRI Mini. The bokeh beyond the field of focus in the background has a so-called soap bubble look to it. This aligns with the simple graphic I just showed you. The foreground is the opposite, a softer orb with darker edges. Take a look here at this point of light at the field of focus. When I roll the focus to either behind or in front of that light, the bokeh circle characteristics change. And that will be true for both types of spherical aberration, over and undercorrected. The background and foreground blur will have opposite characteristics, and thus bokeh will have opposite cross-sectional mapping of intensity. The soap bubble type of bokeh is sometimes called double line bokeh or Nisen Bokeh. It can be considered less pleasing when capturing linear objects in the out-of-focus space. In a lens with overcorrection for spherical aberration, the background can produce these linear double bokeh shapes. Something to consider. Generally speaking, undercorrected spherical aberration is often associated with prettier bokeh. The bright center falling off into a darker area tends to make out-of-focus areas creamier in texture. And in cinematography, we're usually seeing more of the background seen out of focus than the foreground. Unless you shoot a film where you're constantly obstructing your foreground with elements and looking through all of that to the actor, most images are going to have a clear field of view to the subject, and anything behind that subject may fall off, making undercorrected spherical aberration generally preferred. Can we get optimally corrected spherical aberration? In theory, yes. You could get bokeh that is a perfectly blurred circle with no gradation. There would be no change in the bokeh if lens focus shifted an object between background and foreground confusion. However, if a lens designer chases that ideal, they might be making other optical sacrifices in the system. There are some optical techniques that manufacturers have implemented for correcting the bokeh in a lens to be as close to even as possible, via apodization. It's a filter or lens element that has a clear center, but gradually darkens with neutral density tinting as you move to the periphery. Rays going through the center of this filter are unaffected, but rays near the edges are attenuated the most. What it does is smooth out the bokeh into a Gaussian blur or neutral bokeh. For photography, some lenses are sold and manufactured as smooth trans focus lenses. Before you run out to buy or make a filter for your own lenses, the optimal point of correction is by placing the apodization element next to the iris blades. This almost certainly requires it to be placed inside the lens housing, which is why we don't see it often. A lens has to be specially manufactured for this bokeh control. In recent history, there has been an improvement in lens design that could only be manufactured and replicated on a large scale through the use of machine precision. Aspherical elements have improved dramatically since their early mathematical conception. An aspherical lens element looks like a spherical element to the human eye, but its surface curvature is slightly modified so that it has different radii across it, which helps to bring all of the rays into focus on a flatter field. This does a lot to correct for spherical aberration, astigmatism, distortion, coma, and fall-off. The manufacturing process of grinding a precision mold for aspheric elements involves minute scale machining. While our eyes may not see the microscopic turns on the mold surface, those imprints can be magnified and visible in enlarged bokeh. This so-called onion ring bokeh is a fingerprint of an aspherical element used in the lens. With that in mind, you should know that bokeh in the form of an enlarged point source of light can give away a lot of information about your optical system. If you have dust on or inside your lens, that can show up in the bokeh. And now is a great time to move on to a series of tests I shot at CSLA to showcase how the bokeh can be influenced by elements in front of or behind the lens. Here is a classic soft filter. It is made up of a bunch of tiny lenslets for softening an image. When used in a scene with point source bokeh, we can see that the lenslets are projected into these highlights, a Swiss cheese bokeh. Here's one of my black diffusion filters, which has a grid of tiny black points. It's subtle, but you can see that it makes a kind of noisy bokeh that's different whether it's in the foreground or in the background. Here you can see me move a piece of net fabric in front of the lens. And then, if I lock it in place, nets are used to soften images, but it can betray you in the bokeh. And let's pay homage to CSLA for their support. If I just put this here and take a look at the bokeh. CSLA in your image. A field stop is used to cut part of an image. It blocks some of the field of view. This is different than the aperture stop or iris blades found inside the lens, which is generally designed to be at a point in the optical system so that it only acts to shave away unfocused light without cutting into the image. At the start of this video, I showed an example of an artistic photographic technique where people shape the bokeh. This is done with a custom field stop. Here I carved meow into some art card. And it's a bit too wide for this example, but you can see how it shapes the bokeh by cutting into the image field. When I started this test, I used the camera and monitor's false color meters as a way to make sure I was maintaining exposure while introducing field stops. A meter doesn't help here because I don't know how much light loss is in a meow stop. But when I checked the levels, this meow gag is costing me 5 stops of light. Here is a bar pattern I cut and its influence on the bokeh. This has a 3-stop light loss. A field stop can occur behind the lens as well. These Clavius Primes by Gale Optics are known for their swirly bokeh and come with inserts that fit under this removable rear element, which I will absolutely have to clean after this process. Let's drop in one of these unique shapes, this round double disc one. We can see it in the bokeh, but it is incomplete. The pattern is likely too wide for the image circle at the stop and at these edges of frame. This pattern is so restrictive on the light coming in that we have had 7 stops of lost light. That's a lot. That's an f2.8 becoming an f32. The Clavius lenses also have this oval insert. This one eats 3 stops of light. When you look at the effect on the bokeh, at first glance it's kind of reminiscent of anamorphic bokeh. But true anamorphic bokeh is due to the optical elements bending the rays of the image and not solely due to a field stop. There is a small group of filmmakers who do anamorphic faking or anamorfake, and the technique involves using field stops like this to control the bokeh shape. To further fake the anamorphic effect, these filmmakers will use an added element like monofilament line or streak filters to induce streak flares that mimic an anamorphic flare. But the cheating is given away in the bokeh. The film John Wick may have also used a faked anamorphic look on a scene, as shown here. Perhaps this was a pickup shot or they needed a faster lens that wasn't anamorphic. I'm going to show you another test that is tangential to field stops. If we use an object and place it in the foreground out of focus object space, take a look at what happens in the background out of focus space. The tip of this arrow is influencing the shape of the bokeh in the background. And notice how the focused area, the century chart, is not being reshaped by the occluding object. It's darkening, sure, it's losing light, exposure, and contrast, but it's not turning into an arrow shape like the background. And if I take the bar cutout and I move it around, and let's rotate it in different directions, it also reshapes the out-of-focus checkered grid, influencing bokeh. What is happening is that the areas that are not at lens focus, the black and white wall checkers plus the arrow shape, or the wall checkers plus the cutout bar shape, are coming into the optical system as circles of confusion, blobs of unfocused light. Only the focus chart is coming in as sharp points of focused light on the sensor. The mixing of the foreground and background circles of confusion, the blob mixing, if you will, is what is creating those influences on the bokeh. It's like the meow stop or any of the field stops we tested. Shapes in the optical path can impinge upon the out-of-focus circles of light and influence how they are rendered, even if they are not starting as Christmas lights, fairy lights, or anything that would make a large orb bokeh. This is why we generally use a circular iris shape inside of lenses. A circle is the most neutral shape we can achieve that doesn't overly influence the scene. Triangular irises do exist, like in these Arriflex Zeiss B-Speed Primes, and you'll see its effect in the bokeh. This is not a perfect triangle, but a rouleau triangle. Pardon my French. Can you have dark bokeh? Can a dark spot on a white field become like a negative bokeh or anti-fairy light? Let's take a look. Here I've taken a white art card and punched a tiny hole in the middle. I've lit the face of the white card to be close to the highest end exposure the camera can record without clipping, and I've tried to make the area of the circle to be at the toe end of the curve. Now let's roll this out of focus. It disappears. Let's flip this card around and do the opposite. Same exact punched hole and piece of art card, but now the face is underexposed near the toe, and I've put a bright light near the opening to be the same exposure that we had on the white face of the card in the previous shot. And if we roll the focus, we get the blooming bokeh like we did with the fairy lights in the previous tests. Let me show you one more test that I lifted from the pages of the Cine Lens Manual. The Cine Lens Manual, by the way, is a very comprehensive source about lens optics. If you've been watching this far and have been captivated by this video, you'll find a lot of great info in the Cine Lens Manual, a book authored by ASC member Jay Holman and Christopher Probst, ASC. I didn't get my hands on a copy until I was already like 4 months into preparing this video, but when I scrolled through the manual's bibliography and cited sources, I found that we both had referenced many of the same sources in authoritative papers, which was encouraging. Here is a large test with the same concept as the hole in the art card, but bigger. A black arrow on a white field. When we roll the focus away from sharp, the light overtakes the dark and the arrow shape gets skinnier. And now for the opposite. A white arrow on a dark field blooms larger when put out of focus. So we cannot have the so-called dark spot bokeh. Light is a tangible and darkness is the absence of light. When rays of light strike an object, they reflect bundles of rays off and away from that object. If the object is pure yellow, predominantly yellow wavelengths are reflected back, while other colors of the spectrum are mostly absorbed. A dark object reflects less rays because it is absorbing most of the light hitting it, which is why darker clothes make you warmer in the summer sun. So with the arrow and the hole in the card, the white light is reflecting an exponentially higher amount of light rays to the lens than the dark areas are sending. When we roll the focus and make those areas unsharp and turn the light rays into large circles of confusion through the lens, the white light circles of confusion are predominant and have much more light energy and will overtake the darker rays of light being reflected back as the circles of confusion bleed over each other. The light blooms over the darker, weaker rays. I could speak on a lot of other areas of optics. This was a lot of research, but I tried to keep this video focused on bokeh and how it can be influenced or controlled in our work. I hope you found this video useful. I don't think I've done this much research ever, even when I was in college. Please hit that like button if you made it this far. Subscribe if you want to see some more videos like these in the future. Another huge thank you to CSLA for supporting me in this video. If you ever shoot in LA, please rent from them. And as usual, it may take me a couple months to get the next video out because you can see how involved these videos are, but I have to do some work in the meantime. I need to make money. Thank you.